When looking at a new function, so a function that has a certain physical meaning, could be an example from economics, biology, physics, etc. It's important to understand the role of the dependent and independent variables, for now I'll say y and x, and also the interpretation of the derivative and the inverse function, the inverse of the derivative and the derivative of the inverse, because there are various different notations that you might see that you might want to look at and say, well, what does this mean practically? So next we're going to see how to actually deconstruct the meaning of these things, and the key is to look at what the variables are and what the units are, and then interpret those things practically. So for example, suppose I have a function y is equal to f of x, and x has a certain meaning and y has a certain meaning. So associated with x are a given set of units, and associated with y are a given set of units. And then we might be asked to say, well, what is f inverse of 2 equals to 3 represent? Or what's f prime of 0.5 represent? Or what's f prime inverse of 3 represent practically? So when we see notation like this, we should be able to interpret what it means in practical terms. Now there's two main things that you might be asked to interpret, and I like to call these just single nouns all by themselves, or entire sentences. So if you see something like this, f prime of 0.5, that is a noun. If you say interpret f prime of 0.5 practically, you would say f prime of 0.5 represents something. If you were asked interpret f inverse of 2 is equal to 3 practically, you would say, well, this means something. It means that when something is equal to 2, something else will equal 3. Right? So we have a relationship here, whereas over here with f prime of 0.5, we just have a single item. Right? So we're not saying that f prime of 0.5 is equal to 9. We're just saying, what does f prime of 0.5 all by itself represent? And then when we say it's equal to 9, we can interpret that as a complete sentence. We say that this part over here is equal to that part over there. Now to get a handle on this, the inverse, the prime, the inverse of the prime, and the prime of the inverse, I like to draw a map. I like to map it all out. So start off with y is equal to f of x. So here's the function, and then we can invert it, and we get x is equal to f inverse of y. So assuming it's an invertible function, y is equal to f of x is on one side, and then x is equal to f inverse of y on the other side. Now, if you're just given f of x represents something physical, they might not assign the dependent variable y. So the first step would be to assign some variable name for the output and use it, something that will remind you of the meaning of the output. You don't always have to use y. If the output is pressure, you could use P, for example. If the output is height, you could use H, something like this. So now we have these two sides, and we can take the derivative of either of them. So taking the derivative, I'm thinking of that as moving downward. I always, for some reason, think of the derivative as like moving downward. If you have x cubed, the derivative would be 3x squared. So you kind of are moving down towards a lower power. So dy dx would equal f prime of x, right? The change of the output divided by the change of the input, the infinitesimal change of the output over the infinitesimal change of the input is equal to the derivative f prime of x. Now over here, if we take the derivative of this function, it's the same thing, except now the output is x and the input is y. So we have a change of output would be a change of x over a change of y, and this would be f inverse prime of y. So it's the derivative of the inverse function, f inverse prime. So that's the derivative of this function here. So f inverse prime would be a change of x over a change of y. So you can see just by this map, this little chart that I've made, already if I see something like f inverse prime of 27 is equal to 6, I know that 6 represents the change of x over the change of y. Now if I take the inverse of this one, on the other hand, so from here, I can flip this one and say x is equal to f prime inverse. So I guess I'll just move that over here. So if I take the inverse of this and say x is equal to f prime inverse of dy dx, right? Because if I apply the inverse function to f prime, so if I do f prime inverse, it's inverting this relationship right here, which means the input of f prime inverse is going to be dy dx, and the output is going to be x. Right? So basically I see what's happening by just looking at this relationship. So when I take the inverse, I'm just moving the x outside and the dy dx inside. So f prime inverse has an input equal to dy dx and an output equal to x, whereas f inverse prime has an input equal to y and an output equal to dx dy. So you can see the difference, that f inverse prime is not the same as f prime inverse. So writing out these relationships is the first step to interpreting any problem that might ask for these sorts of things practically. Of course, if they don't ask you what f inverse prime is, you wouldn't have to write out this full table. You only have to write out as much as you need to, or that you want to understand. So next we'll look at an actual example where we interpret something practically.